Okay, so we talked about the fact that there's two ways to describe vectors. One is as just a size and direction statement. Here's how big it is. Here's what direction it points. The direction tends to be a very laborious description of so and so many degrees from such and such an axis. And so for that reason, we might want to instead express the vector in two pieces, or what are called components. And I showed you last lecture how to do that. So if you want to break a vector into components, you're going to first need to assign plus and minus. Those are for the components. An x component can point in the plus x or minus x direction. A y component can point in the plus y or minus y direction. And then in order to figure out the size of those components, you're going to need sine and cosine. So if you want to express the two legs of your right triangle, your components, in terms of the whole thing, which is the hypotenuse, you're going to need sine and cosine. What I didn't quite get to last time was how to show you the reverse process. What if somebody gives you something in components, how much you reassemble that? So I think I got as far as giving you the problem we were going to do, but I didn't actually get the chance to do it at all. So let's say that someone gives you a vector in components. They give you the two pieces. The x component is this, the y component is this. And of course, you are going to have to agree with that person on what they mean by x and y. So they're going to have to accompany that with a set of axes indicating what they mean by plus x and plus y. Okay? So let's take a look at the x component. Now that's plus. So that points along the plus x direction. Is that more to the right or to the left, would you say? That is a rightward, of course, because plus x is to the right. How about that y component? Is that more up or more down? It's down because it's negative. So what we are being given is the pieces of a vector that points diagonally rightward and downward, and we're being given the piece that's to the right and the piece that's down, and we are some assembly required here. We're going to have to put these two components back together into the whole. So here's how we do it. Well, it has a rightward piece of plus 10 meters per second. And it has a downward piece of minus 24.2 meters per second. And notice how I put them together. I put them together head to tail. So the arrowheads don't meet, the tails don't meet. The head of one meets with the tail of the other. And then what I can do is so I put add head to tail. And then what you can do to form the entire vector, the prescription is to connect the tail of the first to the head of the last. So like this. So connect the tail of your first component, whichever one you decided to put first, to the head of the last component or second component. So this would be our velocity vector as a whole. And you should always do a head check. Does that point diagonally rightward and downward? Yeah, it does. So common mistakes that people make, stuff like this, right? They take the two components and they put them tail to tail. So if you put them tail to tail like that, you've already lost because there's no way to connect them that's correct. You might say, well, can I connect them like this? Well, no. That vector is up and right. It doesn't have any down piece to it, right? That's not right. What about connecting like this? That's down, but it's to the left. So both ways you have problems, and of course your problem is ultimately stemming from the fact that you put these two vectors tail to tail, and they shouldn't be. So connect them head to tail, and make sure that the vector you end up with has the two pieces that you said it should have. So this is a right piece and a down piece. This points down and right. Okay? Now, we've got that the direction is correct. We need to now get quantitative and figure out how long is this side. Any ideas on how we might get this? Pythagorean theorem, that's right. So this is a right triangle. And the overall size of this vector we get with Pythagorean theorem. Oops, the square looks like it fell down a little bit. There we go. Pythagorean theorem will get you the hypotenuse. I'm going to add that over here. How do you convert from components back to size and direction? Pythagorean theorem is your friend. I should probably say a few brief words about notation because I'm starting to use notation that I haven't formally defined. So for vector notation, this is something that we played a little bit loose with at the beginning when we were pretending we lived in a one-dimensional universe. But now that we're starting to do the real deal, we should make these distinctions. If you see a vector with the vector hat, that's the whole thing. You have to include in your description either the entire size and the direction, because of course both of those are part of a vector, or you can make a list of what the two components are. Okay. I am already starting to kind of cheat and use this right here. Notice that if I wanted to find the size of this vector, I notate it as v without the vector hat. So this indicates the size only. In fact, it's taking this number and just referring to it by itself. It's a handy thing to sometimes do, to say here is how big the vector is without necessarily saying here's which direction it points. In this case, I would find it's 26.2 meters per second. You can use your calculator and verify that. And I do want to explicitly mention that it is always positive. Because remember, plus and minus is for the components. It's not for the whole thing. The direction of the vector as a whole is blah, blah, blah degrees from blah, blah, blah. Okay? So sometimes we just have occasion to refer to the size of it. And that's implicitly positive because the hypotenuse does not play the game of plus and minus. It's the components that do that. If we want to refer to components, we explicitly indicate that it's the x component or the y component. These are the components. And components, of course, can be plus or minus. That's a game that components play. So this will be pretty strictly the notation that I use throughout the course from here on out, and you can always count on it if you see something that it's in this notation. If you see the vector hat, it means the full vector. If you see something that you know is a vector, but it's missing the vector hat, it's because I want to refer to just how big it is without carrying the direction around with it. And if you see an x and y component, x and y subscript, it means it's a component. We were perfectly okay with saying something like this in one dimension because, of course, if you're in a one-dimensional world, plus and minus is the be-all, end-all. But now that we're in a two-dimensional and higher, we would never say this. We might say the x component is that, but we would never say that the vector as a whole was plus or minus, because plus or minus is insufficient for describing direction when there's an infinity of possible directions in 2 dimensions and higher. So there is the length, of course, but this is just the size of it. We should probably find the entire vector. So we've just found that the size is 26.2 meters per second. But to make it a vector, we should figure out how many degrees it is from a nearby axis. And it looks like perhaps the easiest axis to refer to would be the plus x-axis. So it's going to be so and so many degrees clockwise from the plus x-axis. And we need to figure out how many degrees that is. So that's the next and last order of business to figuring out the entire properties of the vector that we got given the components of. So let's do that next. Before I do that, are there any questions? Okay. So I have the hypotenuse already, but sometimes it's nice to not use information that you might have messed up or you might have rounded off accidentally. So let's go back to the original two pieces of information. How might I use these two pieces of information to find the angle? Tangent, right? So we use sine and cosine. Now we need the tangent. So we're on the TOA part of SOHCAHTOA. Tangent of theta is equal to opposite over adjacent. That's always true. That's TOA. Tangent equals opposite over adjacent. Now in this particular case, which side is the opposite side? Is the x or the y component? It's the y component. So in this particular case, it's Vy is the opposite side, Vx is the adjacent. So in this case, those are the components that identify with those particular sides of the triangle. So we can take that ratio. We, of course, have both of those components. But that would only give us the tangent of the angle. We don't want the tangent of the angle. We want the angle itself. So we have to apply a special function whose job it is to kill a tangent and reveal the angle inside. What is that called? Inverse tangent, or arctan, or atan. Okay? So what we're going to do is we're going to apply that function. Of course, anything you do to one side has to be applied to the other side as well. That's the rule for manipulating equations. The atan or arctan or inverse tan is a special function whose whole design is to kill a tan. It's like squaring and square rooting, right? You're back to the same thing you started with. So theta is going to be equal to the inverse tan of Vy over Vx. You want to make sure your calculator is in degree mode. If you are expecting an answer in degrees, if your calculator is in radians mode, you will get the answer in radians or in terms of pi. You should probably be aware what mode your calculator is in. If you do this, your calculator will report to you that the answer is minus 67.5 degrees. Now, what's up with the minus? Well, the minus is your calculator trying to be clever and tell you a little bit about where this is measured from. We don't need our calculators to be clever. And especially sometimes your calculator will try to tell you some results that are bigger than 90 degrees because it seems to prefer the plus x-axis even though your vector is somewhere else. So here's my suggestion to make your life easy. Before you take an inverse tan, always absolute value it. That way you don't have any pesky signs. You will simply get a positive angle, positive theta, between 0 and 90 from some very convenient nearby axis, which you probably, in fact, you should already know from your drawing what axis you're measuring from. I actually had that here from the outset. I knew I was measuring from the plus x-axis. I just wanted to know the amount. So I fill it in. 67.5 degrees clockwise from the plus axis. That is my answer for what does this vector as a whole look like. Being handed the components, I have reconstructed the vector as a whole. Filling in over here, what do you need to do the reverse conversion? You need Pythagorean theorem, and you need inverse tangent. And again, just for convenience, let me remind you to do the absolute value before you take the inverse tan. Then you don't have to mess with any negative angles. You'll simply get a nice positive angle between 0 and 90 from a nearby axis, which you already know from your drawing what it's going to be. So going back and forth here is an indispensable skill. We'll oftentimes go back and forth multiple times in one problem. So again, I can't emphasize this enough. I've mentioned it several times already. Not only will you get some practice on problem number 1 of homework 3, but click on the More Vector Practice link that I've guided you to, and there's like 9 or 10 more examples. Getting the hang of this is going to mean a lot less headache later. So on that more practice sheet, you will find certain things where they give you the components, and then they give you the axes that you should use to reconstruct them. Sometimes the axes are like this, sometimes they're like this, sometimes they're like this. Okay? They can be weird. If you don't like how they look, rotate the paper and do it again. Do it however you like to look at it. And then there are also practices where they give you this and expect you to break them into components, again, giving you the axes that it wants you to do that with. Taking the time to learn this now will prevent a lot of headache, because we will use, you'll see, you'll use it throughout homework 3, homework 4, homework 5, homework 6, all through physics 1, all through physics 2. Okay, so make sure you get the hang of this. Are there any questions before I move on and use these ideas in some physics problems? Okay, so let's do that. I am going to go ahead and before I actually even do any problems, I'm going to just kind of set the stage. We're going to talk about projectile motion. So this is objects flying through the air. We've already, of course, touched this a little bit in homework 2, but it's all been one-dimensional motion. But you know you can throw a baseball or a football in such a way that it moves through both the vertical and horizontal dimensions simultaneously. Here's our playing field. We have the ground, and we generally set x to be horizontal and y to be vertical. Now we know how gravity acts vertically. Gravity gives a constant acceleration that's downward. Here it's notated as negative because I've chosen up to be plus y. And we know that that's how gravity acts. You verified it experimentally at least, and in a couple homeworks we'll get to why it is that value. If we do not consider any other things like air resistance, then in the x direction, how much does gravity do stuff horizontally? It doesn't do anything, right? If gravity acted horizontally, we'd all be falling horizontally toward the wall, right? So gravity, if we're looking at gravity-only problems, right, we're not looking at air resistance. We're hoping it's negligible. If we're talking about gravity only cares about vertical stuff. It doesn't care about horizontal stuff. Now, it is my supposition that the x and y axes of the motion are completely independent. So x and y motion are independent, which means that we can completely think about what a projectile is doing horizontally as completely separate from what it's doing vertically, and we just happen to be observing what it's doing on both, but the two motions are independent. So what that would mean is that we can take a two-dimensional problem and break it up into two one-dimensional problems. We can basically do an x problem and a y problem completely separately. So remember when I said our time spent in one-dimensional land is going to be well spent. Your first two homeworks were all one dimension. Well, now we're going to find that what we need to do to treat multi-dimensional problems is just do basically one-dimensional problems kind of on parallel tracks. So your ability to solve a one-dimensional problem is now going to be utilized twice in the same problem. Now, I realize that this is kind of a big claim that you can do this, and so I wanted to bring in a demo to show you that you can really think of stuff like this in the real world. Okay? So let me clear a little bit of space here. Let's see if I can get this out of the way a little bit. So here's what I have. I have this demo here, which I like to call the drop and shoot. Okay? It's basically a simple mechanical apparatus that lets me simultaneously do two things. It allows me to drop a ball simultaneously to firing one horizontally. So how am I going to do this? Well, this is kind of like a little spring-loaded launcher. You can think of it as kind of coming out of a pinball machine. So this lever, I pull this back, and I can fire something. So if I pull this lever back, I'll put the lever here so I can hold it. And I put something in front of it like this. If I can get it to stay there. Okay. I can fire something off like this. So I can fire it horizontally. That's the shoot part of the drop and shoot. Okay. Now where does the drop part come in? Well, you notice when I pull this back like this, the firing pin actually pokes out the back. So I have a second ball which has a hole in it. And again, it shouldn't bother you that this ball has different mass because we learned that gravity doesn't care about mass, right? So I can also put this ball here, and when I pull the trigger that would shoot a ball out horizontally, it's going to drop this one by pulling the pin out from underneath it, right? So the whole purpose of this thing is to basically fire this one off horizontally and drop this one at the same time. So we're going to do this problem. First I'll show you as a demo, and then I'm going to do it with numbers on the board. So here's my first example of projectile motion. I'm going to have two projectiles, A and B. A is going to be dropped. So it's going to go like this. B is going to be fired horizontally. It's going to go like this, something like that. And here's my question to you. So let's see. Again, don't be shy to weigh in. I want to get a sense if everybody already knows this, then I can go a little quicker. How many people think that ball A is going to land first? The one that's dropped. Okay. How many people think ball B, the one that's fired, is going to land first? How many people think they're going to hit at the same time? Okay, so that's most people. Let's try it. Okay. So I'm going to pull this thing back. I'm going to put one here. Hopefully it'll stay. One here. I think I've got it tilted a little bit just because the ball in the front seems to be rolling off. So there we go. Okay, so probably the best way to judge, it's really hard to watch. It's a lot easier to hear it. So if you hear different times, right? If you hear same time, let's try it. You might need to intercept this one if it's all right. Did you get it? Okay, same time? Okay, this has two settings, so I'm going to fire this thing off even harder. Let's see. You might need to get up to intercept this one. I hope it doesn't fall off. I hope it still stays on the table. Okay. Okay. I think that I heard a slight difference, but it's probably due to the levelness of the table. Thank you. Okay. So they hit the same time. The reason why they hit at the same time is because everything that they have going on vertically at the beginning is exactly the same. They both have no vertical velocity, right? This one has no vertical velocity because it has no velocity at all, right? It just dropped from rest. This one has a horizontal velocity, but that's completely independent from the fact that it has no vertical velocity, right? It's not, has no component vertically upward or downward. It has nothing going on vertically to start with, just like ball A. So hopefully this demonstration indicates that we really can take something that's seemingly complicated like this and just break it up or decompose it into two simpler one-dimensional problems. So that's the next order of business, is let's just go ahead and add some numbers to this problem. Actually, before I do that, are there any questions? Okay, so let's add some numbers to this. I'm going to go ahead and say that my hypothetical drop was 30 meters. Of course, that's way bigger than what I had initially, or on this demo, but it's a nice round number. And let me say that ball B is fired off at 10 meters per second horizontally. And let me just pose a series of questions about this. In let's say part A, this is like a hypothetical homework question. It's very much like the homework questions you actually have. What's the flight time of A? What's the flight time of B? So part B, how far from the base of my cliff does B land? So I know that B flies away from the starting point horizontally. I want to know how far that is. And then I want to know what's the final velocity of A and the final velocity of B. And what I mean, of course, by final is not do they eventually stick in the mud where they land, but I mean impact speed, right? So what's the velocity that gravity can give them before they hit the ground? So this is the impact velocity. And I'm going to show you that we can answer these questions by just thinking of the flights as two one-dimensional problems like this. Okay? So let's go ahead and do that. I'm going to have to clear a little space over here. So let's start with doing the flight time of ball A. This could have been on homework too, right? It's a basic one-dimensional thing. I'm going to set some axes. I'll say x is forward and y is upward. If I want to know the flight time of A, is that an x question or a y question? It's a y question. In fact, A doesn't have anything going on. Ball A doesn't have anything going on in the x direction. So I'm going to obviously set my variables like this. I'm going to talk about the y direction. Put down my 5 variables in no particular order. What's my initial y velocity? 0, because dropped it from rest, so there's no velocity of any kind. What's my acceleration? Negative 9.8. It's negative because I set upward to be plus, so anything downward is negative. How about my displacement? Minus 30, right? It falls down, and down is negative. Just like this was negative, this is negative. So don't forget, everything that you're putting in, the plus and minuses, are according to the axis choice that you set. If up is plus, anything that's down is negative. Can I set the final velocity to be 0? Definitely not. That would be the final velocity gravity had a chance to give it before it hit something else and had a different acceleration. I'm looking for time. Which equation would I use? Does anyone remember? Number 2, right? The one that's missing the variable, don't know, no care about. Uh-oh, equation number 2, solving for time. Got a yellow alert for a quadratic equation. Got a last-ditch effort. One of these better be 0. Okay, good. It is. We do not have to use the quadratic. Okay? If you look at the equation, looks like this. This whole part is going to go to 0 because I dropped it from rest, right? So how do I solve for the time? I solve for t squared and square root it, right? Just give you the answer here. Try it yourself at home. Make sure you can get this. Practice your math if necessary. And the answer will be about 2.5 seconds. That is the total flight time of ball A. Okay, let's do ball B. For ball B, what is the displacement in the vertical direction? What's delta y? Negative 30, right? It also drops through a height of 30 meters, right? What is the initial y velocity? It's 0, right? This velocity, the initial component in the y direction is nothing. It's all x plus 10 meters per second in the x. So there's no part to that velocity which is vertical. Okay? What's the acceleration vertically? Negative 9.8. This is the same, this is the same, this is the same, this is the same, just like we saw in the demo, right? The fact that it happens to be moving horizontally at the same time has no bearing whatsoever to the y direction. We already saw in the demo that the flight times were the same. The setup's the same, the answer's the same. Okay? Everything is the same in the y direction. Okay? Are there any questions on that before I move on to part B? Okay, so let's do part B. I'm asked for this distance right here. Do you think that's an x question or a y question? It's an x question, okay? So if part A happened to be a y question, I should mention, by the way, that it's not always a y, but it most of the time is. And the reason why part A was a y question is because the thing that determines when the flight's over is a vertical consideration. When you've fallen off your cliff and you hit the ground, when you've dropped 30 meters, flight's over, right? If there was a wall that you hit on the horizontal, then you might use the horizontal axis to find the time, right? Because there's something in the horizontal that's constraining when the flight's over, when you hit the wall. But in this case, the thing that determines how long the flight has a chance to go, it's the 30-meter drop, right? Once you're done with the 30-meter drop, the flight has to be over. So that happens to be a y question. Part B is an x question. So let's do that. So part B, here's what's going on. It's traveling horizontally. Now, I don't need to draw the whole thing, right? I'm thinking of the motion as in two pieces, and this is the horizontal piece. It just travels to the right. And I'm going to put down my x variables. You can see, by the way, why I tried to pick up the good habit of putting subscripts on everything. Y's when they're y and x's when they're x, because now we have both of them going on at the same in the same problem. And the last thing you want to do is accidentally plug in a y variable for an x variable or vice versa. You've got to keep them straight. Okay? So this is where understanding components is really important. Understanding how to sort your problem into your two bins, your x problem and your y problem, and not crossing your streams. Okay, so what's the initial x velocity? Plus 10. Right? So there you see it, right? Your initial velocity for ball B, it's plus 10 in the x and 0 in the y. Okay? It has no y velocity to start with. It has only x velocity to start with. So make sure you understand why the x and y components are different. What is the acceleration in the x direction? 0. Gravity doesn't care about horizontal motion. Gravity doesn't make it go faster or go slower. So, what is the final velocity in the x? Still plus 10, right? If you don't have any acceleration, it can't change. So Vx is constant because the acceleration is 0. So any x velocity that you have during a flight, it came from the beginning of the flight and it persists throughout to the end of the flight. Gravity can't change it, so it is whatever it is at the beginning of the flight all the way through to the end. Now we're looking for this, but we do have a problem. I know it looks like we have our required 3 pieces of information, but the fact that the acceleration is 0 will completely decimate the constant acceleration equations. You can try plugging in 0 into the constant acceleration equations and you will not have much left. Okay? For example, equation number 1, v final equals v initial plus a t. If the acceleration is 0, we get the super obvious statement that the velocity is constant. It doesn't help us in any way. That's the definition of 0 acceleration. How did that help us in any way? It doesn't help, okay? Let's take equation number 2. It looks like this. Equation number 2, this whole term is wiped out by the fact that the acceleration is 0, and we get what's basically distance equals rate times time. If you do this with 3, 4, and 5, the last 3 equations, you'll get repeats of these. So all 5 equations reduce down to one thing that's of any use whatsoever, and it's this. It's essentially distance equals rate times time in the x direction. And I implore you to not have to reinvent the wheel in every problem. Don't do this. Just use this. So really what these projectile motion problems are, and this is the majority of your homework 3, is y stuff, which is identical to your homework number 2, plus this equation. This is what you use on the horizontal. Okay? That's basically it. And notice what this equation says. It just basically says that how far you go will be determined by your x velocity, which you have throughout your launch. Remember, gravity doesn't care. And so the one thing you will need to do is to supply how much time you're going to spend with it. There's no limiting factor for how far you go in the x direction. There's no wall to hit. There's no nothing. So if you want to know how far you have a chance to go to the side, you're going to have to give it some information about how long you're going to let it have the 10 meters per second. You're going to have to borrow the time from the y direction. So the one quantity that's shared, the x and y share the time. Okay? Because of course, if you've gone 5 seconds in the x direction, you've of course also gone 5 seconds in the y direction. You can't travel at different rates of time in the horizontal and vertical, right? The time is the common index by which you're working on both your tracks, right? Your x and y tracks are linked by the fact that they're happening in the same timestamp. In fact, of course, there really isn't a separate x and y motion. That's just our way of simplifying it for our brains. It's really one motion that we are thinking of as 2 independent tracks. Be prepared to share the time either way. There is a couple homework problems where you have to get the time from the x and put it in the y. Okay? And if you're not sure how to take all your information and combine it, I'd say this, the best way in physics is to just carefully write down everything and then see where you can get a toehold for the algebra. So write down your y setup, write down this equation, carefully track what you have and don't have, and you should see a way through. Okay? So in this case, I go ahead and I say, I know I have a x velocity of 10 meters per second, and my y direction has said I have 2.5 seconds to spend it before the flight's over, and I can go ahead and find that my x displacement is 25 meters. So that's how far of a chance I have to go to the side. So I go ahead, I can label it in the diagram. This distance is 25 meters. That is the horizontal distance that B had a chance to travel. This distance is sometimes called the range, or R for short. This very setup that we're looking at right now, you're going to use it in your lab this week. It's not going to be quite the same. It's going to be slightly, if ever so slightly, modified. Here's what you do. In your lab, you know that the flight time will be the flight time no matter how fast you fire this off or don't fire it off at all. The flight time is the flight time. But what you guys will do is you will measure the range and use this equation to work backwards to what is the speed at which it was fired, right? Because if something is fired off faster, it'll travel further in that time, and if something's fired off slower, it'll travel a smaller range. So you guys are actually going to work backwards to how fast does your projectile launcher fire. You guys will be working backwards from measuring the range to determining the firing speed. Once you have the firing speed of your projectile launcher, you can fire it off any which way and be able to calculate where the object should land now. So that's going to be my very next problem, is I'm going to take a projectile launcher, and instead of just firing off horizontally, I'm going to fire it off at an angle. So something like a baseball throw or a football throw, something that's going through the air like this. Okay? The only other thing I wanted to do on this problem, before I do that, is talk about the shape of this thing. Now this may seem like a complicated arc shape, but the arc simply comes about because of the features of the x and y that we've discussed already. So over here, oh, I forgot to do part C as well, so I'll do that real quick. So A falls like this, of course, right? Its velocity will increase. Its y velocity gets faster because gravity goes ahead and does that. How would you figure out the y velocity? Well, you just use this setup, right? You just solve for v final instead. Let me tell you what the result is. The result is minus 24.2 meters per second. That's its impact speed. So again, same setup as part A, but solve for the final velocity instead. Now everything that ball A does vertically, ball B does too. So when ball A is falling this much, so is ball B. When ball A hits the ground, we saw, so does ball B. Everything matches identically. However, remember that there's also an x velocity, right? So we can see why the arc forms the way it does. The arc shape simply forms from the fact that the x velocity is constant, because gravity doesn't change it, while the y velocity is increasing, right? It's going faster. So if we reassemble those, we can see why it curves over, right? And at the end, what's the y velocity at the end? Minus 24.2 meters per second, same as the other one, right? Everything was identically in the y direction. What's the x velocity? Plus 10 meters per second. Gravity can't change it. It's the same throughout the flight. That's where the arc shape comes from. It comes from the x velocity staying constant while the y velocity continues to grow. If these sound familiar, it's because we reassembled them to start the day. If we want to find the final impact velocity of B, we would say that it's either a 10 meters per second x velocity and a minus 24.2 meters per second y velocity, or of course we could reassemble them as we did, 26.2 meters per second, 67.5 degrees, and I guess I'll say a little more informally, below horizontal, okay? So there I have my impact speed is actually 26.2 meters per second, right? That is the speed when I account for what it's doing both horizontally and vertically. So ball B certainly strikes faster than ball A because ball A only has a y component to its velocity, whereas x also has a horizontal component, which makes the hypotenuse larger. Okay, so let me see if I can get through one more example, and then that'll cover us for projectile motion. Once we've done it once, it's quite quick to do it again. My second example, I'm going to fire a ball into the air at an angle. The speed of the firing is 5 meters per second. The angle will be 30 degrees. And I can ask such questions as, how high does it go? What's the total time of flight? We can again ask for the range, and we can ask for the impact speed, or impact velocity. And I'll try my best to talk about all of these. Let me draw the flight here real quick. It's going to look like this. So for part A, how high does it go? I probably want to set the final point at the top. And let me put down my y variables in no particular order. Of course, it's a y question, which means how high does it go is exclusively a y question. And I really want to know what's delta y. Now my initial y velocity, not all of that velocity is directed to the side, or directed vertically. So I'm going to have to break up this velocity into how much is directed to the side and how much of it is directed vertically. If this is ringing some bells, it's because this was the very vector that I showed you how to disassemble into components. You can look back in your notes, and it'll tell you exactly how we arrived at this. And we find that despite throwing this at 5 meters per second, only 2.5 meters per second is actually directed vertically. And that is what, of course, our gravitational acceleration is going to start chewing on. And we're interested in how long does it take to reach the top of the flight where, what's the final y velocity at the top? 0. Is the entire velocity 0? No, but it's got no more y velocity. In fact, what's the velocity right there? Same as the x velocity doesn't change. So the x velocity is plus 4.33 meters per second at the top of the flight, but no y velocity there. Gravity took it off, chewed it up. So you can go ahead and solve here. Sorry, what did I want? I wanted, ignore the time actually, sorry. I wanted the height. The height is plus 0.32 meters. And so I have the height for the time of flight. Let me just see if I can do this relatively quickly, because I don't want to leave you hanging in the middle of the example. Here, same initial y velocity, same acceleration, looking for the time. Y velocity isn't 0 anymore, right? You're falling. You don't come to a stop. What's the displacement, though? In the y direction, it's 0. I'm not saying you land at the same place, but I'm saying as far as the vertical direction concerned, you did. You can get that the final the flight time is 0.51 seconds. Try it yourself at home. If you want to know the range, again, don't start from scratch. Use this. Your plus 4.33 meters per second that was directed to the side is what you have to spend your entire flight with. right? And then you get the a range of plus 2.2 meters. So this distance right here is 2.2 meters. And finally, your final velocity is really easy, because what's happened to the x velocity? It's the same. And what do we learn happened on level ground? When you landed at the same level you started, what happens with your y velocity? It's the same, just downward instead of upward, right? So this triangle is the exact same thing as you had before. This is going to be 30 degrees, and this is going to be 5 meters per second. You land at the same speed you launched with, and the angle above horizontal becomes the angle below horizontal. So if you wanted to express the final velocity, you might say it's going to be now 5 meters per second, 30 degrees below horizontal. You basically have your y component got chewed up and then re-added while your x component stayed the same. This projectile shares all the same features as one that was launched vertically at 2.5 meters per second. It's got the same height, same flight time. The only difference is it happens to be drifting to the side simultaneously. Okay, so that's it for today. Sorry I went a little long. That should do it for the majority of your homework number 3.